So we discussed what minimums and maximums are, absolute minimums, absolute maximums are. But we want to know how to find those minimums and maximums. Of course, you have calculators these days, computers, right? You can graph it and you can exactly determine where the maximum or minimum is going to be. Just by graphing, I'll show you how to do that later on. But there are cases you want to find it without using a calculator. Or it could be a case where there is a maximum on a really, really small scale, which you can't see using your calculator. So the purpose of calculus here, or derivatives, is if you follow the process, you will know exactly where to search for a minimum or a maximum. Yes? So instead of going back and forth, changing all kinds of values in your calculator, all you have to do is follow the process and it will tell you exactly where the minimum or maximum is going to be. So this is more like a guide of being very smart and effective. So I'll take a very simple case. Where is it maximum? Right here.
Since there's four, we can't do relative.
That is correct. So there, let me just say this is the number 8.
Well, we already
I'll call it f of 8.
Okay, so what we're saying is we don't know the y value associated with it.
Yeah. I mean, I can come up with one, but amazing. So there is a maximum at x is equal to 8. We want to make use of the derivative to give us that information. So what happens to the derivative as it gets closer and closer and closer to that point?
It gets closer to 0.
Closer to 0. Exactly at 8, it would become 0. Correct?
So what we can say at the very least is that these we won't have to work backwards from a derivative. Is that what integral is? Just working backwards from a derivative? Oh, that's interesting.
So the points say where f of x is 0 or undefined
So wouldn't it be f?
does not exist is what we call the critical value or number, critical number. Yes.
Wouldn't it be f prime of x?
Okay. F prime of x is 0. So we're pretty much going to do it in a backward sense. You looked at this picture and to the naked eye at 8, you guys mentioned the derivative is 0. But in practice, suppose you don't have a graph, all you have to do is take the derivative, set it equal to 0, solve for x, and that is going to give you the critical value. Yes, the critical value is going to tell you whether the function is going to have a maximum or a minimum. Good. So, a critical value need not exist. There are cases where it won't. We will do some of those, but if it doesn't exist, it doesn't imply that there is no maximum at that point. For instance, suppose you have a curve of that sort.
Are we going to be given the derivative?
No, we have to find it. Now, does this particular graph have a maximum?
That's it.
Yes. Up to. This is a Laplace density. So 2, there is a maximum value. Great. Derivative. Do you think that there is a derivative up in that corner?
Yeah.
I hear yes from Gio, no from Lewis. So yes or no?
Could you repeat your
So at
question?
that point, can there be a derivative?
At 2, is there a derivative
Yes,
at 2?
I don't, you get the derivative.
Yes. it's just going to be equal to 0.
Because for the function that's the of x, technically, there isn't, there isn't good.
Very good. The derivative does not exist for this particular function. Keep in mind, when we first did derivatives, I mentioned that we need continuous functions or functions that have smooth turns, right? It has to be smooth. Here, it is a sharp turn, right? It's what we call a cut. So you can't have a derivative here. Likewise, you cannot have a derivative when you have an infinite discontinuity. You cannot have a derivative at an endpoint. Can you tell me why? So this is, really sharp. It's a cut. Derivative does not exist. However, the critical value is still 2 because the derivative doesn't exist. Yes, because there is a maximum. With me? So, which is why I said the derivative is 0 or it doesn't exist or it is undefined. The endpoints. Would a derivative exist at an endpoint? Yes or no? James says no.
No.
Why not, James?
It had infinite amounts of tangent lines there.
Well, you could have infinite amount of tangent lines. What a wonderful answer. Is it right?
Sounds right.
Sounds right. Thank you for that. Right. I could draw infinitely many tangent lines at that point. No, it doesn't exist. Another answer. For a derivative to exist, what must exist? Huh? No. No. Going back to the definition of a derivative. Before we got to the derivative, we wanted to learn something. So that has to exist for a derivative to exist.
We've been using derivatives at the very least like instantaneous forms.
James, a limit. A limit has to exist for a derivative to exist. Would a limit exist at this endpoint?
No.
No, because for a limit to exist, we need 2, both the left and right-sided limits to match. It doesn't, there's only 1. So anytime we talk about derivatives, we always define it on an open interval. So this is a case where you have a global maximum, and the derivative is going to give us a valid critical number. We can use that critical number to come up with that maximum. This is a case where the derivative does not exist. However, the value where it doesn't exist corresponds to a maximum. Good. Now, you can always use a calculator to look at the picture and come up with the maximum value or verify your answer. That's right. Okay.
Well, thank you for the explanation, sir.
So, I'm going to start with something simple. I believe your book calls it as critical number. I'm used to calling them as critical values, doesn't matter. F of x is equal to x minus 1 squared. So what is the process behind finding a critical value? 1. The very first step. Look at that, James.
Foil it out and then.
Foil it out.
Find a derivative.
Find the derivative. Should I foil to find the derivative?
No.
No, why not?
You don't need it.
Chain rule, easy. So f prime of x would be 2 x minus 1 multiplied by 1. Sure, I can foil it out, but it's that extra work, right? I don't want to do that. 2. Set the derivative equal to 0. Which would imply 2 times x minus 1 equals 0. Divide by 2 on both sides. X minus 1 would equal 0, which would imply x is equal to 1. Is it a valid critical value? Yes, it's a number. So x equals 1 is a critical value. So I'm going to say that this particular function is going to have a minimum at x is equal to 1. Now pick up your calculator, graph that, and see if there is a minimum at x is equal to 1. Did we see a minimum at x is equal to 1?
Yes.
Yeah, X.
So if you graph this,
So 2 X minus 1 is the first time.
Yeah, and x is equal to 1.
so that's what the curve is going to look like. So there is a minimum at x is equal to 1. Is it an absolute minimum? Yes.
Oh, yeah. My question is, sir, would we not be able to use this process if we were talking about something like, at the very, basically where it has a lot of different points at which the slope will be 0?
Yeah, we can. So if it is a well-defined function, and if you have multiple values, for instance, a sine wave, right? If you do the math properly, you can determine every single maximum or minimum for a sine wave.
No, true.
So,
I'm using this.
How many global maximums does, I mean, should I even call it a global maximum? Does an absolute maximum exist for a sine wave?
No.
No, because it hits maximum and minimum values, infinite maximum and minimum values, they're all relative to an integral. So for us to say that a function has a global or absolute minimum or a maximum, it must be the lowest of all low values here, in this case, hence absolute. Does that make sense? Gio?
So if you grab the derivative, it's like a straight line through the minimum. So like in this case, when there's only one, like maximum, will the derivative always go through that point?
It will go through, but in what fashion?
Decreasing.
It's gonna go that way. So Gio's question was, if there is a derivative, you drew that line, that's going to go through that point, sure, but in what way? Exactly at one. I'm not asking as to what happens past one, I'm asking exactly at one. 0, it has to be flat. Right? That is the entire point of setting this equal to 0. So it is flat because it's going to touch and turn, so the derivative is flat. Sarah asked me, well, how do you know that it is a minimum? There is something called a first derivative test. If you understand finding critical values, determining the minimum and the maximum would be easy. To your eyes, when you look at this, you call it a minimum, but what makes it a minimum? What is your thought process behind this?
It's the lowest value possible.
It is the lowest value possible. Okay, one way of looking at it. In terms of directions, how about that?
The point at the very least where it turns from a negative slope to a positive slope.
Negative slope, positive slope. Every single tangent line that you draw to the left of the critical value will have a negative slope. Every single tangent line that you can draw to the right of the critical value will have a positive slope. Negative to positive would imply a minimum. Positive to negative would imply a maximum. Good. That's what we call a first derivative test. I'm not going to start that today. When we come back next time, we want to do a few more problems on critical values. Because there are some functions where you could have more than one critical value. A good example would be a function of that sort. You look at that function, when you graph it, do you think that the function would have exactly one critical value? Two, because there is a point where the derivative would become zero, which is like that. Another point where the derivative would become zero, there. So there would be two critical values. So once we know where to look at, we can then go use our calculator to verify our answer. Good. Now, if you don't understand the process here, there are certain functions with which you cannot simply use a calculator and determine the critical value. No matter how hard you try, your eyes can't see it. But if you use the process properly, and if you get the critical value, you can look at the exact minimum or maximum. Which is why I say this is just a guiding tool to find the minimum and maximum. Good. Good place to start.